Hello again, method students. In this video, we're going to go through the chain rule, which is a really commonly used rule in calculus and very handy when we are trying to differentiate something that I guess isn't already written in expanded form. So far, we've looked at differentiating things where we just can work through one term at a time. And the chain rule is helpful in situations where we can't easily do that. So at the start here, we've just got this note about if you had a function like x cubed plus 1 all squared, well, one way you could differentiate that would be to expand the brackets and then differentiate term by term, and that wouldn't be too bad to do using the rules that we know and knowing how to expand brackets. But if you had to differentiate the function f of x equals x cubed plus 1 to the power of 30, you certainly don't want to be sitting there expanding brackets for all that time just so you can differentiate term by term. The chain rule comes in really handy here. The chain rule is a rule that says dy dx, so if your original function is y, then dy dx, the derivative, will equal dy du times du dx. And this has just some really nice sort of properties here. Like you can kind of see that knowing what you know about cancelling fractions, this rule just intuitively makes sense because dy du times du dx, well, I've got a du on top and a du on the bottom. And it's pretty easy to see, I think, that the right-hand side equals the left-hand side in this formula. What I guess we have to understand is where does this u come from? And the u comes really from just making a substitution to make the function look a little bit nicer, and we've done that in lots of ways in other sections of maths as well. So let's get stuck into a couple of examples. In this section, we're also going to show you like a shortcut for using the chain rule, which comes in handy because the more you practice it, the quicker you want to get at this sort of thing. Okay, so example 9 says differentiate f of x equals 3x plus 4 to the power of 20. Again, no way you want to be expanding brackets there. You'll be sitting there for half an hour before you can even do the differentiation. So what we do is we say we're going to let u equal 3x plus 4. And therefore what's going to, I guess, happen is that our function becomes y equals, I'm going to use y instead of f of x just because that's how it's written in the chain rule, y equals u to the power of 20. Okay, now in the chain rule, what I need to have, the two pieces are dy du, which is the derivative of y with respect to u, and I also need to have du dx, which is the derivative of u with respect to x. And from this first one, I can say, okay, well, if u equals 3x plus 4, I can work out du dx, no problem. That's just the derivative of 3x plus 4, which is 3. And if y equals u to the power of 20, well, I can differentiate that as well. dy du, which is the derivative of y with respect to u, well, just multiply by the power, subtract 1 from the power. It's 20u to the power of 19. Okay, and then I can go, all right, well, there's two things that differentiated really easily separately. The chain rule just says I've got to bring them back together. So dy dx is equal to dy du, so 20u to the power of 19 times du dx, which was 3. Okay, so that just equals, well, 20 times 3 is 60, so 60u to the power of 19. Except we just use u as like this sort of arbitrary substitution, so like you often have to do when you've made this substitution just to make your life easier, at the end you've got to undo it because u is actually equal to 3x plus 4. And so we could say, and I'm going to flip this now back to, even though this was dy dx, the question gave us f of x, so let's call the derivative f dash of x equals 60u to the power of 19, but that's really 60 times 3x plus 4 to the power of 19. And that's our final answer. So really what the chain rule's done there is given us something that's pretty tricky to differentiate, right? But what we've done is we've just split it into two things that are really easy to differentiate. And that's kind of the beauty of the chain rule, okay? Because doing it any other way would have taken a long, long time. So that's a quick example of how the chain rule works. What I might do is I'll show you the shortcut method in another video, but I hope this gives you an idea of how the chain rule works and how it can be, even though we haven't used the shortcut method yet, how this can still be quite a big time saver.